Welcome back to the deep dive. Today we're really zeroing in, taking a magnifying glass to a huge engineering challenge, but one that's got tiny environmental details wrapped all through it.
That's right. We're diving into the engineering plans for managing a major modern facility, specifically the Al Shamal City landfill.
And these aren't just, glossy brochures. We're looking at highly technical sources here.
Exactly. Detailed engineering documents outlining very specific strategies for mitigation and impact management. It's all about the targets, the technical fixes.
So our mission today is to unpack that, to understand how an operation this big goes beyond just, piling up trash and actually starts managing its environmental footprint, down to the smallest measurable bits.
Mm-hmm. And we should start with the core idea here. Mitigation. What does that even mean in this context?
Good point.
So mitigation, basically, it's all the actions you take to limit or reduce or even offset the negative environmental effects that you know are going to happen or might happen.
And the way they approach it here seems very structured, systematic, like a formula almost.
It is. It's a pretty standard but crucial three-step process. It sets the priorities for everything.
Okay, what are the steps?
First, number one, you avoid impacts completely if you possibly can. Prevention first.
Right. Stop the problem before it starts.
Exactly. If you can't avoid it, step two is to minimize or reduce the impact. Get it down to the lowest practical level using engineering or operational controls.
Okay, avoid, then minimize. What's step three?
Step three is compensate. For whatever impact is left over, the unavoidable stuff, you have to make up for it somehow.
Yeah.
Usually through restoring habitat elsewhere or some kind of environmental offset.
Avoid, minimize, compensate. Got it. And this whole framework, it feeds into a bigger picture, right?
Absolutely. It's directly supporting Qatar's national environment and climate change strategy, the one running from 2021 to 2030. So this isn't just about one landfill. It's part of a much larger national strategy for sustainable waste management.
Okay, framework established. Let's get into the specifics. First big challenge. Liquids. The leachate.
Ah, yes, leachate. It's essentially, garbage juice, highly contaminated liquid that drains through all the waste, and it's notoriously difficult to manage.
The number one risk, I'd imagine, for soil and groundwater.
Definitely. Our sources say Al Shamal produces about 1,445 cubic meters a year.
Okay, 1445, how much is that day to day?
It works out to roughly 4 cubic meters every single day.
4 cubic meters, so like 4,000 liters daily of liquid packed with metals, ammonia, organics, stuff you really don't want leaking out.
Precisely, which is why the technical solution has to be robust. It's all about the barrier system.
What does that involve?
It's a composite liner system. Think layers. High-density polyethylene HDPE combined with a layer of engineered clay.
Okay, like a really heavy-duty pool liner?
Sort of, but much more advanced. The key is the permeability requirement. It has to be incredibly low. The standard is Ka 1A10 meters per second. Basically, it needs to be as watertight as solid rock.
Wow. So that contains it. That's the avoid leakage step.
Right.
But you still have 4,000 liters a day collecting inside that liner. What then?
Right. Containment isn't enough. You need management. The liner system includes perforated HDPE pipes, like a drainage network, that channel all that leachate to a collection point, a sump.
And from the sump?
From there, it goes into treatment. But interestingly, a good chunk of it is actually recirculated back into the landfill waste itself.
Recirculated? Hang on. Why would you put the contaminated liquid back in? Seems counterintuitive.
It does, but it actually serves two main purposes. One, it helps speed up the natural decomposition and stabilization of the waste, gets it to a more inert state faster.
Okay, speeds things up. What's the other reason?
It also helps manage the volume. Some of the liquid evaporates within the waste pile, reducing the amount you ultimately have to treat externally. Speaking of reducing volume, another critical tactic, still under that avoid category, is diverting stormwater. Keeping clean rainwater out of the active waste areas means you produce much less leachate overall, less clean water mixing with waste.
Makes sense. Less water in, less contaminated water out. And how do they know this whole system, the liner, the drainage, the treatment, is actually working?
Constant monitoring.
Okay.
They have monitoring wells strategically placed, and they're regularly checking key indicators, things like pH, chemical oxygen demand, or COD, and ammonia levels. If anything spikes, they know there might be an issue.
Right, keeping a very close eye on it. Okay, let's shift from liquids to gases. Section 2 in our sources deals with greenhouse gases, potential energy use, and safety. And the big one here is methane, CH.
Methane. Yeah. It's always the primary gas concern for landfills. The decomposition process naturally produces it. At Al Shamal, the estimate is around 975 kilograms of methane per day.
975 kilos a day. That sounds like a lot. And methane is potent, right? Much more than CO.
Oh, vastly more potent. The sources highlight this. It's considered 84 times more powerful as a greenhouse gas than carbon dioxide over a 20-year time frame. So capturing it isn't just good practice, it's critical for climate mitigation.
And locally, it's also a hazard. Fire risk.
Absolutely. Methane is flammable. If concentrations build up, you have a serious risk of fire or even explosion. So the mitigation strategy has to be aggressive on both fronts, environment and safety.
How do they capture it then, if it's being generated throughout the waste?
They use a network of wells, vertical pipes drilled down into the waste, and horizontal collectors laid in as the waste is placed. These are all connected by pipes to a vacuum system.
A giant vacuum cleaner for methane, essentially.
Yeah, you could think of it like that. It actively sucks the gas out of the waste meth.
And once they've vacuumed it out, do they just vent it?
No, definitely not. The current main approach is controlled flaring. They burn the methane off in a high-temperature flare stack.
Why burn it?
Because burning methane converts it primarily into carbon dioxide and water. Co-Euro is still a greenhouse gas, obviously, but far less potent than the methane was. The flare has to be super efficient, though the requirement is over 98% destruction efficiency.
Okay, so flaring is the current solution, but is that the end goal?
No, that's more like the minimum standard, the immediate safety measure. The long-term strategic goal is to use that captured gas for waste-to-energy, or WTE.
So actually generating power from it.
Exactly. Move from just neutralizing the hazard to creating a resource. That's the aim.
I like that the plans have these really specific targets. What are they aiming for with methane capture overall?
They're aiming high. The target is at least 90% capture efficiency for the whole gas collection system.
90% capture. Wow.
And that should lead to an overall reduction in methane emissions of at least 70%.
Huge numbers. How do they ensure they hit those targets and manage the safety side?
Well, besides the active collection system, there are operational things too, like compacting the waste really densely as it comes in, which reduces gas pathways. And covering the active working phase with soil daily helps cap surface emissions. Plus, continuous monitoring for methane levels, especially around the flare and collection system, to make sure concentrations stay well below 25% of the lower explosive limit, the LEL. Safety valves, automatic shutoffs, it's all built in.
Okay, that covers methane. But flaring still produces CO-Euro. You mentioned converting methane to CO-Euro. How much are we talking about?
Yeah, even with efficient flaring, there's still Kyotos. The total estimate is around 184,656 tons over the landfill's life, which averages out to about 6,155 tons per year.
Still a significant amount. How do they mitigate that?
There are a few strategies. First, if and when they implement the waste-to-energy plan, using the gas on-site avoids emissions from burning fossil fuels for power elsewhere, that's an offset.
Okay.
They also rely on nature-based solutions, planting trees and shrubs as windbreaks and green buffers around the site perimeter. These plants naturally absorb co-Euros as they grow.
Right. Basic carbon sequestration via plants. But I remember reading something much more high-tech in the plans. Almost surprising for a landfill.
Yes. This is where it gets really interesting. Looking towards the future, the plan actually includes developing the capability to capture the Kyoros from the landfill gas stream.
Capture the CO itself,
Yeah.
not just flare the methane.
Right. Capture the Euro and then store it underground permanently. It's called geological sequestration.
Geological sequestration at a landfill. I usually hear about that for like power plants or heavy industry.
There's definitely advanced thinking for waste management. The idea is to purify the Euro and then inject it deep underground.
Into what? Where does it go?
They're considering two main options. Either into depleted natural gas reservoirs nearby, basically putting carbon back where fossil fuels came from, or into deep saline formations.
Saline formation.
Yeah, these are vast, deep underground layers of porous rock that are saturated with salty water. They have huge potential capacity for storing Euros safely for, well, geological timescales.
That's a major leap, turning a landfill into potentially a carbon storage site.
It really is. It shifts the whole paradigm.
So what does this mean for their CO targets? Is there a number attached to this ambition?
There is. The overall target is to get the operational Euro emissions down below 6,000 tons a year. But the really striking part is the specific goal for sequestration. They aim to eventually store at least 10% of their captured carbon underground via this injection process.
10% stored geologically.
Okay.
That's a statement. It suggests the facility isn't just managing its waste problem, but actively trying to contribute to carbon removal.
Precisely. It's a long-term vision, but it's embedded in the engineering plans.
Okay, mind-blowing stuff on the gas front. Let's pull back a bit to the day-to-day reality on site. Section 3 in the sources covers site operations, worker health, and safety. Back to that avoid, minimize, compensate framework. First up, dust.
Right, dust control. Always an issue on large sites with moving vehicles and earthworks. Air quality concern. The sources give specific emission figures, about 2.188 tons of total suspended particulates, TSP, per year, and 0.65 tons of the finer PM Euro particles.
How do they tackle that? Is it complicated tech?
Mostly operational tactics, falling under avoid and minimize. Pretty standard, but needs to be done rigorously. Lots of water spraying on haul roads, excavation areas, stockpiles, especially during dry, windy conditions.
Water helps keep the dust down. What else?
Strict rules for vehicles. All trucks carrying waste or soil must have their loads covered, and probably the biggest one, a site-wide speed limit. Vehicles have to stay under 20 kilometers per hour.
Slow speeds make a big difference for dust.
Huge difference. Less churning, less dust kicked up. They also schedule activities around the weather, meaning they avoid major excavation work during periods of high winds, specifically if wind speeds get above 10 meters per second. Just wait until it calms down.
Right, all adds up. Is there a specific reduction target for dust?
Yes, the goal is to reduce TSP emissions by at least 50%, aiming to get below 1.1 tons per year.
Okay, dust managed. What about the people working there? Landfills must be tough environments. Noise, heat.
Extremely tough. The baseline measurements show average noise levels around machinery hitting 94 decibels, dBA. That's very high, well above safe long-term exposure limits.
And the heat, especially in Qatar's climate.
Intense. The measure they use is wet bulb globe temperature, WBGT, which counts for heat, humidity, sun, and wind. The baseline can reach about 42 degrees Celsius WBGT during hot periods. That's into the extreme risk category for heat stress.
So how do you protect workers? This falls under minimize exposure, I guess. You can't eliminate the noise or heat entirely.
Exactly. Minimization is key. First, personal protective equipment PPE. That means mandatory use of things like dust masks and, crucially, ear protection like earplugs or earmuffs.
Standard PPE. What about the heat specifically? That seems like the bigger immediate danger.
It requires a multi-pronged approach. Constant supply of cold drinking water is essential. Providing shaded rest areas near the work zones is another must. But the most critical part is managing the work itself.
How so?
Implementing structured work rest cycles, particularly during the hottest parts of the day or year. You can't just have people working continuously in those conditions.
What kind of cycle are we talking about?
The sources specify a strict 45 minutes of work, followed by a mandatory 15-minute rest period in the shade. This cycle is enforced during high heat conditions.
45 on, 15 off. That breaks up the exposure significantly. And the targets, what are they aiming for in terms of worker exposure?
The targets are set at recognized occupational safety limits. For noise, it's to reduce the average exposure over an 8-hour shift to below 85 dBA. And for heat, to manage conditions and work cycles so that worker exposure stays below a WPGT of 32 degrees Celsius, much safer levels.
Okay, makes sense. Protecting the people on site is paramount.
Now, let's talk about something you can't always see but can definitely sense. Odor. Yes, odor nuisance. Often the #1 source of public complaints for facilities like this, even if everything else is technically compliant.
So how do you manage something as subjective as smell? You can't just measure it with a simple meter, can you?
Not easily, no, which is why they have to rely on predictive modeling. The sources mentioned using the Gaussian plume model. It's a standard air dispersion model that predicts how pollutants, in this case, odorous compounds like hydrogen sulfide, H2Os, will travel and dilute downwind.
Okay, so they model the H2Os dispersion. What did the model predict for, say, the nearest residential areas or a typical boundary distance?
They looked at a distance of 500 meters from the source. The calculated H2Os concentration came out at 1.3 parts per billion ppb.
1.3 ppb. Now, is that high, low? What does that number actually mean in terms of someone smelling it?
Good question. You need the context of human perception thresholds. The detection threshold for H2Os, the point where a sensitive nose might just pick it up, is very low, around 0.5 to 1 ppb.
Okay, so 1.3 is above the detection threshold.
It is. But then there's the recognition threshold, the level where people generally notice it and identify it as that characteristic rotten egg smell. That's higher, typically between 2 and 30 ppb.
So 1.3 ppb is in that tricky zone. Maybe not strong enough for everyone to complain, but definitely detectable sometimes.
Exactly. And because it's above the lowest detection level, the mitigation plan kicks in. They can't risk nuisance complaints.
So what's the target? How much do they need to reduce it by?
The modeling showed they need to reduce the source discharge rate, the Q, in the model by about 60%. That would bring the concentration at 500 meters down to zero point 0.5 ppb, right at the bottom edge or below the detection threshold.
60% reduction. How do they achieve that?
Through a combination of operational techniques. Some are pretty straightforward, like fast burial, getting waste with high odor potential, like food waste or fish market waste, covered over quickly. Don't let it sit exposed.
Makes sense. Anything else?
Yes, using geotextile covers over areas of the landfill that aren't currently active. These aren't gas-tight like the final cap, but they can significantly reduce surface emissions, the sources say, by around 50%.
Okay, quick burial, temporary covers. What's the most effective tool?
The most powerful tool is the active gas collection system itself, the same one capturing the methane.
Ah, the vacuum system.
Right. By actively pulling gas out of the waste, it dramatically reduces the amount that can escape passively through the surface. That system can cut odor emissions by up to 90% from the areas it covers effectively. So combining all three, quick burial, covers, and active extraction, allows them to hit that necessary 60% reduction overall.
Keeping the smell literally under wraps or sucked away.
Okay.
We've covered liquids, gases, dust, noise, heat, odor. Feels like we've hit all the major environmental engineering points.
Yeah.
High-tech liners, advanced gas capture, sequestration plans.
Pretty comprehensive. But there was one more item in the sources, something quite unexpected.
Unexpected how?
It relates to a very specific, very local ecological factor, truffles.
Wait, sorry. Did you say truffles? Like the expensive fungus? We were just talking about geological sequestration of corals, and now we're on truffle management.
Bizarre, right?
Yeah.
But yes, it's mentioned specifically in the mitigation requirements. It's a fascinating example of that compensate principle applied hyperlocally.
How does a landfill impact truffle growth? And what do they have to do?
Well, the landfill construction itself obviously disturbs the immediate area, but the surrounding land might be potential habitat for desert truffles, which are culturally significant and harvested locally. The plan acknowledges this.
So it's about protecting the potential habitat nearby.
Exactly. It requires them to work with local stakeholders, specifically truffle hunters, to identify and map known or likely truffle spots in the vicinity.
Okay, map the spots, then what?
Then they have to implement avoidance measures. Things like making sure truck routes and any temporary access tracks steer clear of those sensitive areas, minimizing soil compaction near known spots, and also ensuring that traditional access for the hunters isn't blocked during the truffle season.
Wow. So alongside managing methane emissions to parts per million, they also have to ensure haul trucks don't drive over fungus patches.
It really shows the breadth of what environmental impact mitigation can cover.
Yeah.
From global climate change down to protecting a local culinary and cultural resource, it's quite something.
That really is a spectrum. Okay, let's try and wrap this up. We've gone through the engineering plans for Al Shamal, and it's incredibly detailed. We're talking about managing, 4 cubic meters of toxic liquid a day?
Nearly a ton of methane daily.
Capturing that methane with 90% efficiency, planning to store cocoa underground, controlling dust down to the ton per year, managing noise and heat for worker safety.
Modeling odor down to parts per billion.
And ensuring trucks don't disturb truffle habitats. It's
Right.
mind-bogglingly complex.
It really drives home the point that modern landfill management isn't, just digging a pit and hoping for the best. It's highly specialized engineering, multidisciplinary, and it operates against very strict, measurable targets for every single potential pathway of pollution or impact.
And for you, the listener, this deep dive really underscores something crucial about large infrastructure projects. Building the thing is just the start. The real marker of success, especially now, is how thoroughly you plan for mitigating the impacts. With numbers, with targets, with specific technologies.
Absolutely. The planning has to be just as rigorous for the mitigation as for the construction itself.
So let's end with that provocative thought you raised earlier, tied to the Kyogyur sequestration.
Right. The fact that a facility like this is seriously planning for geological storage of carbon dioxide, potentially using deep saline formations. What does that tell us about where waste management might be heading?
It suggests a future role far beyond just containment, doesn't it?
It really does. Could waste facilities become active players in global carbon capture, not just minimizing their own footprint, but actually helping to clean up legacy emissions by providing storage infrastructure? It's a fascinating question about future responsibilities.
Turning a liability into a climate asset. Something for you to think about. That's all for this deep dive. We'll see you next time.